Hi everyone. Have you ever wondered how scientists can tell the difference between two samples of the same element like carbon or oxygen just by looking at their isotopes? Or how these tiny differences can unlock secrets about tracing water sources and movement, understanding the formation conditions and sources of the mineral deposits, Earth's climate history, and even the origins of the solar system? Well, today we are diving into the fascinating world of stable isotope fractionation. This is a powerful tool used in various fields of science, from geology to biology to environmental studies. But what exactly is stable isotope fractionation and how does it work? Okay, so in simple terms, stable isotope fractionation refers to the process by which different isotopes of an element are distributed among various chemical substances and physical states. This distribution can provide valuable information about the processes and conditions that created the materials we study. Don't forget to like, subscribe, and hit the notification bell so you never miss out on our deep dives into scientific concept. And if you have any questions or topics you'd like us to cover, drop a comment below and we will be happy to assist. So let's get started and explore the incredible world of stable isotope fractionation in geochemistry. So today's outline, we're gonna talk much about what are exactly are isotopes and stable isotopes per se, and why are some of these stable, and of course, we want to know as well why are they important, and we're gonna now move to how and why does fractionation occur, and then now show you the real world example of how scientists use the stable isotope fractionation in their research. Okay, so let's remind ourselves that the isotopes are atoms of the same element. Isotopes are atoms of the same element that have the same number of protons but different number of neutrons. This means when that happens, it means they have different atomic masses. Okay, now why would they have different atomic masses? This is because in the nucleus of an atom, and that's where we have protons and neutrons. Okay, so if the what's in the nucleus differs, it means the atomic masses would differ. So let me give you an example when we talk about the isotopes. Let's take a close look at carbon 12 and carbon 13. Okay, so you'd agree with me that carbon 12, it would have 6 neutrons, and this one, it would have about 7 neutrons. So you can now see that when we have the same number of protons, but now the only thing that will differ, it will be what you call the neutrons. So when the neutrons are different, it makes now the atomic masses, or there's the atomic masses to be different, which is why we say the isotopes atoms of the same element that have the same number of protons but different number of neutrons. And when that happens, it makes these to have different atomic masses. Okay, but now then what is exactly a fractionation? To fractionate in simple terms, it just means to separate. Okay, so this is the process of separation of two isotopes of an element during natural occurring processes as a result of their mass differences. Okay, or the bond strength. All right, so in terms of the mass differences, we know that when we compare light lighter elements and the heavy lighter isotopes and the heavy isotopes. For example, let me just stick to our example, yeah, carbon 12 and carbon 13. I mean, light isotopes would be this carbon 12, and then heavy isotope, it will be this carbon 13. Okay, so these things, they've got the same analogy with when people are running. All right, those that light, they would move fast. Okay, so if this is the finish line, if this is the starting the starting point, I mean, the heavy ones and the light ones, they are from the same point, but the one that will reach the finishing line will be the lighter, because the person has less weight, and then they'll be able to move faster, and then they'll reach the finishing line first, as compared to heavy ones. So is the lighter isotopes, such as carbon 12, they move slightly faster, and now not only that, but they also react more readily than heavier isotopes, such as carbon 13 in this example. Okay, so these things, they get to be seen especially during the physical processes such as evaporation or the diffusion. So processes like evaporation and diffusion would always favor lighter isotopes, because they require what you call less energy. They require less energy, okay, to move into a different phase. So lighter isotopes, they require less energy to move to different phase. Okay, for example, moving from liquid to gas during what you call evaporation. Okay, so that's what that's why fractionation happens. It happens because of what you call the mass differences. But now, in terms of what you call the bond strength, we know that the the bonds involving lighter isotopes are generally slightly weaker than those with heavier isotopes. So it means heavier isotopes, they've got strong bonds, and then they would move slowly, and that is to say, they would react slowly. But the lighter isotopes, their bonds are weak, and then they would react faster than the heavy isotopes during chemical reactions. Okay, for example, if I were to give you example of what you call a photosynthesis, okay, a process through which the plants manufacture their own food, okay, through the help of light. Okay, so we know that plants, they prefer the lighter carbon 12. Okay, they prefer the lighter carbon 12 isotopes because it forms slightly weaker bonds. So make it when this has what you call slightly weaker bonds, this make it easier for the plants to just incorporate that carbon 12 into what you call their organic molecules. Okay, so these things, this process of fractionation, it happens in our everyday life. Okay, but if I were to give you another example now, if I were to give you evaporation, I mean, we know when water evaporates from the ocean or from any volume of water, okay, the lighter isotopes such as oxygen 16, they evaporate more readily than the heavier ones, which is why the ocean during evaporation will always be enriched with heavy isotopes, because during evaporation, the lighter ones, because they move faster, they react faster, and they have less bonds, and then they get to evaporate and then enter into the gas phase. And then the heavy ones, they're the ones that they will be enriched into the solid phase. So these are the processes which are happening in our everyday lives. Okay, so isotope fractionation is a process when stable isotopes of an element are being partitioned or separated from each other during chemical reaction or physical process such as evaporation. Okay, so the natural process that contribute to the fractionation of isotopes include but not limited to an increase or decrease in temperature, okay, or the chemical conditions such as change in the oxygen fugacities and also what we call the pH. Okay, so Yes, so what it's exactly this isotope fractionation, as already mentioned, that this fractionation is just about separation, okay, and then it depends on what you call the bond strength and also the mass differences, as I've explained. Okay. Okay. So, for example, when we compare especially during evaporation and of course condensation, if we were to compare the oxygens, okay, well, the oxygen isotopes, oxygen 18, it's a heavy isotope, and oxygen 16 is the lighter one. So it means during evaporation, oxygen 16, it will be the one that is entering the gas phase, and then oxygen 18, it will be enriched in the solid state. All right. And then now during the condensation, which is just the reverse of evaporation, it means when the vapor condenses now to form rain or snow, the heavier isotopes such as oxygen 18, okay, would condenses more readily. So precipitation, it will always be enriched in heavy isotopes such as oxygen 18, but then compared to the remaining vapor. So the remaining vapor, it will always be enriched in lighter isotopes. So it's just the reverse of the process called evaporation. Okay. So we have different isotopes. We've got those of hydrogen, we've got those of hydrogen, oxygen, carbon, and sulfur. Okay, so each and every isotope, it has its own application. For example, I was giving you an example of photosynthesis about this carbon, and then also about also oxygen and hydrogen that are releasing during evaporation and condensation. And then, of course, sulfur isotopes, they are used just to track the movement. Okay, basically they are mostly applied during what you call the ore deposits. Okay, they're being applied in ore deposits, and mainly they're used to understand the formation conditions and the sources of the mineral deposits, because the sulfur, it has got the capability to track, okay, its path. Okay, so yes, so sulfur isotope is important for understanding the formation of magmatic, hydrothermal, and volcanic, or the VMS, volcanic massive sulfide deposits. Okay, and then oxygen is important for understanding the processes that take place during the formation of mineral deposits, and then also not only that, but also for the evaporations and stuff. So carbon isotopes are fundamental in dating geological materials and understanding the Earth history. Carbon 14 dating is widely used to determine the age of organic remains such as fossils and archaeological artifacts. Hydrogen isotopes help trace the movement of water in hydrogeological systems. So by analyzing isotopic composition in water sources, scientists can track water origins, pathways, and their interactions in ecosystem, groundwater, and the atmosphere. But I will still show you when we'll be talking about the real application of the stable isotopes. Okay, so bear with me and stay tuned. So the mechanisms, the physical processes that makes the fractionation of stable isotopes to be possible. Okay, those processes, we include evaporation and condensation. This one I've already explained it. And then, I mean, of course, we already talk about the fact that the lighter isotopes, they would always move faster and they would react more readily than the heavy isotopes. Okay, so it means these processes, it can be melting or crystallization or diffusion, adsorption and desorption. These processes, they would because they would always favor lighter isotopes. Why? Because they would require less energy, okay, to move into a different phase. Okay, so I hope it makes sense. Okay, so now, because for example, if we were to talk about if we were to talk about melting and crystallization, I mean, we know when we are melting some, let's explain it in terms of the phases. When you are melting, you are just moving from a solid into into the liquid, but when you're crystallizing, you're just moving from the liquid into the solid. So this would have the same analogy with what was happening during evaporation and condensation, of course. So moving right on, so we've got the ratio, and then we've got what we call the fractionation factor. Okay, so the ratio is basically what we use to express the ratio of heavy to light isotopes. So if you can check here, we've got the heavy oxygen 18 to the lighter oxygen 16. So the ratio is just a convenient way of expressing the ratio of heavy to light isotopes. But now these ratios are normalized using the standard symbols and expressed as the delta notation. But I will show you the standards usually used mostly in hydrogeology and also in sulfides deposits. Okay, yeah. So we have to normalize these things because one, they must be expressed in terms of what we call per thousand, because if you don't express them in terms of per thousand, those ratios, those values will be significantly too small, and then you cannot be able to interpret them. And then so if you want to interpret them, you have to normalize them and then also express them into per thousand. But I'm going to show you in a few as well. Then now if you have now those ratios and you normalize them, then it will be a good way of describing the degree of fractionation in terms of the isotope ratio, okay, in two different phases or reservoirs. But now, on the other hand, we've got what we call fractionation factor. Okay, this is just the ratio between the product and the reactant. So if we can check here, we've already mentioned the fact that we've got what we call the ratio, just expressing the heavy isotopes to the light isotopes as I've explained. Then we've got two phases of where in this case we've got what do you call melting, and then we know upper mantle when it probably when it undergoes what you call maybe it can be wedge melting, and then we're gonna form a magma. So these are two phases, the solid and the melt. Okay, so these ones will be the reactants, then this one will be the products. This is because the more you are partially melting the upper mantle, the more you're going to produce the magma. So what's happening is now the concentration, the fractionation factor, it uses the product, the ratio of the product and the ratio of the reactant. Okay, so the isotope ratio in the resulting component of phase, then the isotope ratio in the initial reservoir, like here. That's what reactants are for. Okay, and then yeah, so these are just the formulas, and then as of the ratio I've already mentioned it. That is just the expression of the heavy isotopes to the ratio of heavy isotope to light isotopes. Okay, so factors influencing the sign and magnitude of fractionation factors are the temperatures, chemical composition, the crystal structure and chemical bonds, and of course pressure. But pressure is less important. But the most important thing is chemical composition and the temperature. So for example, the temperature is very crucial in controlling the isotope fractionation. For example, during evaporation, if especially close to equatorial regions, those areas that they receive high amount of sun rays, they would they would experience high, because of intense heat, they would experience high evaporation. Okay, yes, so this is the same analogy. Let me give you the real example. Let's say your kettle. Okay, let's say your kettle. So if you plug your kettle and then you turn it on. And then obviously the particles, because you've given them the energy, they would start to be excited, and then they would start to jump, okay, at the bottom of the kettle. And then in no time, then now separation or fractionation will start to happen because of this of this temperature. And then now at the same time, because of the chemical composition, we know heavy isotopes are preferentially partitioned into the elements with small atomic radius and large ionic potential. Okay, for example, the carbonate minerals are rich in oxygen 18 because the heavy oxygen is partitioned into the small, highly charged. Okay, carbon 4 plus, somehow important in controlling the isotope fractionation. Okay, so in terms of crystal structure and chemical bonds, that is also less important. So we're gonna focus mostly on the temperature and the chemical composition. But there are also these things such as the crystal structure and chemical bonds and pressure. They are also very important. Okay, in controlling what you call the fractionation. Okay, so it is easier and more precise to measure the difference in absolute isotope ratios between two substances than the value of isotope ratios. So it means now, how can you do that? Because if the values, if you don't normalize these things, if you don't express them in terms of per thousand, those values, they would be significantly too small to be understood. Like it would be something like 0.00000000007. Now you can't interpret this, so it will be a difficult way of interpreting the data. Then now, for geologists to be able to understand now these values, they need to express them. Okay, stable isotopes are commonly reported as deltas. You need to express them in terms of the delta values units. Okay, or of parts per thousand or per mil. Okay, relative to appropriate reference standards. So you multiply by 1,000. So if you multiply by 1,000, by so doing, you say you are in per mil. Okay, so now the data, it will be now an easier thing to be interpreted. Okay, now can now see that we also have got our standards. We also have our standards. So the standards are many, but I'll show you the different standards per different applications. I mean, hydrogeology would have different applications than in the ore deposits, and then in other applications. Okay, so this is how you have to normalize your isotope ratios. So when we're talking about the standard samples, for example, for the sulfides, for those people that are studying sulfides, especially in the Bushveld complex, they usually use trolite. Okay, what do you call canyon diabylo iron meteorite? Okay, this is a very standard sample used for reporting the sulfur 34. Okay, and then those that will be studying hydrogeology, they use what you call standard mean ocean water. Okay, and then but now for reporting what you call the carbon, we're using what you call PD belemnite formation, which was found in South Carolina in USA. So you can now see that for different applications, you have to use different standards. So I would urge each and every one of you, especially the researchers, if for example, because my master studies about the sulfides, so I'm using the trolite. All right, so but those that are doing hydrogeology, they would use different standards. All right, yep. So for example, hydrogen, okay, the standards can be Vienna standard mean ocean water, and then for the carbon, you can use what you call a PD belemnite, okay, which was found in PD formation, and then for the nitrogen, you can use N2 in the atmosphere. Then for the oxygen, you can use Vienna standard mean ocean water as well. And then means these, okay, the people for the hydrogeology, they can use the Vienna standard mean ocean water. And then for the sulfur, you can use canyon diplo-trolide. Okay, you can use what you call canyon diplo-trolide. All right, so for all these sulfides, there are sulfur isotopes, and then the most important ones are these ones. That most important ones, especially to track the formation of O deposits. Okay, so you can use that one. So yeah, this table has been adopted from Prof. Isaac Tesema at the University of Limpopo. Okay. So what are the implications of the delta values? Now we have expressed our ratios in terms of the delta values. Now they are readable. They are they can now significantly be interpreted. Okay. Now to differentiate what you call natural variations. Okay. Sharp. Now we now need to understand what would now those delta values mean. A positive values of a delta means enrichment, all right? And the negative, it will mean depletion. Simple as that. Okay. For example, a sample with the delta value of negative 10 per thousand is depleted in oxygen 8, and the ratio of oxygen 18 to oxygen 16 is now depleted. But now, if it is positive, it will be enriched. But obviously, we always compare our result because remember on that formula we have normalized everything to our respective standards. So because, for example, we know everyone internationally, we always, our standard, especially for height, we always use what you call the sea level. So we always say 10 meters away from the ground. So is these isotope ratios. So we always express them relative to the standard, which is why we say it's a depleted, okay, in these ratios, okay, by 10% or 1% relative to the standard sample. We always express our results to what you call the standard. A zero delta value implies no isotope fractionation. There wasn't any separation. Okay, I hope it makes sense. I hope it makes sense. Yeah, so now we looking at the final part wherein we are checking the real world example of the stable isotope application, and especially for the fractionation part. Okay, so the stable isotope fractionation provides invaluable insight into the geological processes and earth history. Okay, remember, we as geologists, we always want to understand our past. Okay, we always want to understand our past, and obviously the geological process such as contamination, assimilation, and many other processes. So by examining the ratios of stable isotopes in various materials, scientists can reconstruct the past climates, trace water sources, study geochemical cycles, explore ore deposits, reconstruct ancient diets, and understand the volcanic system. And they are not only limited to this. Okay, so the list is endless. But now, I choose plus minus. I think it's the plus minus 4. Hydrogeology, paleoclimatology, the also the volcanology, okay, and many other real applications. So in terms of paleoclimatology, we use this for studying the ice cores. Okay, so I've separated these things in terms of the objectives, the method, and okay, the inside. So the objective is to reconstruct the past climate. We want to understand what was happening, what our climate was like in the past. Okay, so the method, the scientists analyze the ratios of oxygen isotopes, okay, and then in ice cores extracted from the glaciers and the ice sheet. Okay, so we take the ice cores from the glaciers and the ice sheets, and then we gonna now analyze these isotopes. Okay, now the ratio of these isotopes varies with temperature. Higher values of oxygen isotopes in ice cores typically indicate warmer periods. Wow. While lower values suggest colder periods. Now, can you see that, oh, we weren't there maybe 10 million years ago, we weren't there, but we by analyzing or by using the oxygen isotopes, we can understand the past climates. That okay, so if we get the higher delta oxygen isotopes, okay, we know that oh, the climate was warmer, and if we got something lighter, then we know that okay, it was a bit colder. So it means by studying these variations, scientists can infer past temperature changes, climate conditions over hundreds of thousands of years. So in terms of hydrogeology or hydrology, we want to trace water sources and movement. So how? So the objective would be to understand water cycle processes and groundwater sources. Okay, want to know the recharging or what recharges the groundwater. All right. So we know in terms of hydrogeology, we know that the surface water it's interconnected with with the groundwater through what we call the pore spaces. Okay, so usually the surface water will always recharge the groundwater, provided we've got the sufficient porosity and the permeability, okay, to allow the interaction between the two reservoirs. Okay, so it means in hydrogeology, we know, guys, that if we have got the places that they've got sufficient amount of rivers, sufficient amount of dams, so the likelihood is we've got sufficient amount of groundwater below because of the surface water. They recharge the groundwater. And again, if also if we've got the flat topography, we know the water. We've got the flat topography, and provided we've got vegetation there, we know now the water won't undergo what you call the runoff. Then they will be able to infiltrate sufficiently, and then they would recharge the groundwater. So now the method would obviously use the hydrogen and oxygen, okay, because as mentioned, these people, they for the standards they use the Vienna, okay, a standard mean ocean. Okay, now what do? We're gonna sample the water from the rivers, from the lakes, and from the groundwater. Okay, so and then after sampling that, we're gonna analyze that the groundwater. So we keep the water nicely in smaller containers, and then you make sure they are not exposed to oxygen, and then you keep them in good temperatures, room temperatures. All right, and then yeah, so after that you take this for the analysis. So different sources of water like rainfall, snow melt, and groundwater have distinct isotopic signatures. So by comparing these signatures, scientists can trace the origin of water in watershed, understand the contribution of different sources to river flow, and study the recharge and the movement of the groundwater. Okay, so in terms of petrology and mineral exploration, this is my area. I'm using the isotopes for especially for the mineral exploration. Okay, in the Bushveld complex, especially the northern limb. Okay, yeah, but nonetheless, this is for the ore deposit formation. It's for the ore deposit formation. We want to understand the formation conditions and the sources of the mineral deposits. Okay, so then we usually use the sulfur isotopes, but you can also use the oxygen, okay, and the lead isotopes. But yeah, so these are sulfur isotopes because I mean sulfur, it has got the capability to track. So it's like a fingerprint, a human fingerprint. So a human fingerprint, even if you were to leave your fingerprint somewhere, maybe and then you go somewhere far by checking at your fingerprint, we will track where you are. Okay, so the sulfur isotopes, they are like fingerprints. They do that. Okay, they can be able to track the path. Okay, so sulfur isotope ratios can reveal the sources of sulfur. Okay, and the conditions of formations. Okay, oxygen isotopes in quartz and other minerals can provide information on the temperature and origin of fluids involved in ore deposits. Lead isotope can trace the source of metals and the age of mineralization and mineralization events. In the end, volcanology, so wherein we are studying the magma sources and evolution, and then we can use what you call the strontium, neodymium, and lead. Okay, so different metal and crystal sources have different isotopic signatures. So by analyzing these isotopes in volcanic rocks, scientists can infer the contribution of various sources to the magma, cracked magma, differentiation processes, and of course understand the evolution of volcanic system. So yeah, this brings us to the end of our lesson on stable isotope fractionation. I hope you have learned some things. So if you you have any questions on the topics you'd like us to cover, please drop a comment below, and then we will be happy to assist. All right. So above all, don't forget to like, subscribe, and hit the notification button so that you never miss out on our deep dives into scientific concept. You don't have to miss anything. You must always be updated, and of course show us appreciation by like, sharing, and then of course always subscribing if you are new to this channel. All right, thank you guys for joining us today. Your support is your support means a whole lot to us. And then I will always say, until next time, cheers.